All right. Sorry, sorry for the slight delay. I just had to set up everything. Welcome everyone to this year's course on data structures and algorithms, 9024, semester 2, 2018. Just a few words about myself. My name is Michael. If you've always wondered how to pronounce my second name, the correct pronunciation would be Tilscher. But this is easy only for German speakers, so you can just call me Michael as always. My office is on level 4 in the CSE building K17. Here you've got my phone number and my email address. I do offer 2 consultations, one right before this lecture in my office and the other one on Thursday from 11 a.m. to 12 noon. If you want to see me during these consultations, just come up to level 4. If the door is closed, then you have to pick up the phone and dial this internal number that is shown here on the slide. And of course, I'm also running a forum, and you can always ask questions on the forum as well. My research focus is on artificial intelligence and robots, and I've got a particular interest in general problem-solving systems and general game playing. And my hobbies are, I like to read fiction, I like to go to the movies, films. I really like to eat, preferably non-German food. Just last week I was invited at the National Chengchi University in Taipei, and I went to 2 different night markets where only local people go, and I had absolutely fantastic street food. I also used to enjoy football. I see I don't have to talk about this anymore. It was a great disaster. So let's just move on and see what's going to happen in 4 years' time. My other favorite team, the Australians, they did reasonably well in the World Cup as well. So, but yeah, we don't want to talk about the World Cup at all. Let's talk about who else is involved in this course. We have 2 tutors, Shanush and Michael. We do offer a help lab on Fridays from 1 to 3. The exact location is building K14, lower ground 20. Attendance is entirely voluntary, but in particular if you have never programmed in C before, and I will talk about homework a little later. If you have difficulties with writing programs in C, then you're very welcome to come to this help lab, use one of the computers, and there will be one tutor around who's going to answer any questions that you might have. We also have a course administrator, Michael Schofield, and you might receive emails from him on admin matters. Let me see if that works. No, that doesn't. So I'll have to click here. Yes. Now, with regard to this course, the goals for this course are that if you compare it to Comp 9021, which I assume almost everyone here has been attending, most likely just last semester, this course gets you to think like a programmer. It gets you to solve problems by developing programs and express your ideas, your programs, in the language Python. Now, Comp 9024 is not just a continuation of this course. It rather puts a focus on more the scientific aspect of programming and solving problems as a computer scientist. We will learn about the fundamental data structures and algorithms that every computer scientist needs to know about. You will learn how to reason about the applicability and the effectiveness of different data structures and algorithms so that you know which one to choose for a problem at hand. You will be able to analyze the efficiency of algorithms and programs, and we will be using the programming language C. I will say more about this programming language and this choice a little later. So that's basically the difference between these courses, 9021 and 9024. As always, a picture says more than 1,000 words. So let me illustrate the difference between these courses by two pictures. This is not going to work very well. So I picture you as taking your first programming steps in Comp 9021. Very cute. So that would be you in the last semester, and this would be you in this semester. So you're really advancing to a state where you can feel like a real computer scientist. As you can see, there will be blood and tears involved, but in the end, hopefully, you will feel like a matured programmer. The preconditions for this course mostly come from Comp 9021. At the start of this course, I expect you to be able to produce correct programs from a given specification, to understand the state-based model of computation, that is, the state of a program can always be summarized by the state of all the variables in the program, and when you perform a statement in a program, then it changes the state of the entire program by changing some of the variables. So you would know about variables, you would know about assignments of values, computing expressions and assigning the resulting value to variables and function parameters. You should also be familiar with fundamental data types and data structures, such as characters, numbers, strings, arrays, also linked lists, although we're going to go through them again, and binary trees, although, again, we will deal with binary trees in much more detail in this course. I expect you to know fundamental control structures, such as conditionals, if then else, and loops, such as while and for. And you would have learned to fix simple bugs in incorrect programs. At the end of the course, you should be able to choose and develop your own effective data structures for a problem at hand. Should be able to analyze the performance characteristics of different algorithms. Choose and develop algorithms on the data structures that you either choose existing ones or develop your own ones. You should be able to package a set of data structures and implemented functions for these data structures as an abstract data type. We will be talking about what we mean by abstraction and encapsulation a little later. And as I said, we will be learning how to develop and maintain programs written in the programming language C. The major themes are data structures. When we talk about data structures, we mean ways of storing data inside a computer for efficient use. And sometimes we will see it depends on what you want to use data for, in which way you should store them in your computer. We will be looking at algorithms, and as you know, an algorithm is a step-by-step process for solving a problem with the restriction that we always have a finite amount of space and time. That is, we expect our algorithms, our programs to terminate. The major themes are data structures on the one hand, with the focus on, for example, graphs and trees. A variety of algorithms will be looked at, for example, on graphs, on trees, on strings. And we will be looking at the analysis of algorithms, how efficient they are. For some data types, such as graphs, we will be looking at alternative data structures, different ways in which they can be represented in a computer, and different implementations based on these data structures. And for algorithms, we will be looking at complexity analysis. Access to the course material. I suppose you all have looked at the web page already. All course information is placed on the main course website. You do need to log in with your ZID to access material, also to access the lecture recordings that will be made available usually within half an hour or 1 hour after the lecture. And if you want to use the web interface to submit assignments or ask questions on the forum, then you have to log in, and you can also use WebCMS to view your own marks. I assume that since this is not your first semester, for most of you at least, you would already know how to do that. Here is an overview of the schedule. We are now in week 2. We will start with an introduction, obviously, and then a very quick introduction to the C programming language. We will then look at abstract data types, which I've mentioned earlier, and dynamic data structures. So the first 4 weeks, they will be focusing on data, and the rest will be focusing on algorithms, and then data structures for these algorithms, with the main focus on, as I already said, graphs and search trees, as well as text processing algorithms, that is, algorithms on strings. At the very end, depending on whether I have time or not, I will also introduce you to randomized algorithms. You see here on the right-hand side these cryptic numbers. They refer to chapters in the 2 textbooks that I'm recommending. There is a supplementary textbook, A Nice Introduction to C Programming, if you haven't programmed in C. That would be the Moffat book, indicated here by M. So M10 means chapter 10 in the Moffat book. And then there is Sedgwick's textbook, and the corresponding chapter is shown here. You can also see that we will start with a help lab right this week. So the first help lab for the first homework, you can attend this Friday. We will have 2 programming assignments. I expect to release the first assignment in week 4, and you can see it's then due in week 6, and the second assignment will be released in week 8, and is going to be due in week 11. You will also see that there is a midterm test in week 8 from Monday 12 noon to Tuesday 12 noon. Wow, 24 hours testing marathon. No, this is not what it means. It means there will be this 24-hour time window in which you can, at your own time, do this test. And this test will be done online. And I will say a few more words about this just a little later, as well as closer to the test time. But do keep that date in mind, Monday to Tuesday. You can do that online. That is, you don't have to be here at the university. You can do it at your own time. But you should be available during that time for at least 1 hour. Just a few thank yous from my side. Just like I asked you to do this, in particular in your assignments, always give credit when you use someone else's work. The lecture that I'm delivering actually for the second time. My first time to deliver this lecture was last year. I've been borrowing a lot of material from various different sources, slides by John Shepard and 2 other lecturers at my school. I've been borrowing, obviously, material from the 2 textbooks by Sedgwick and by Moffat. And I've also been borrowing some material from Introduction to Java, Data Structures and Algorithms in Java, as well as a nice book on programming challenges, from which I adapted some of the challenge exercises for the homework. So coming back to the textbook, this is going to be the main textbook for this course, which actually consists of 2 different volumes, part 1 to 4, and part 5, which focuses on graph algorithms. They are very good books. We won't be able to go through all the chapters in this book. Some material is not necessary, because you've already learned this in 9021. But there's more algorithms and more data structures than I can possibly cover in this lecture. And for this book is pretty useful beyond even this course. The only thing that I don't really like about this book is the coding style. The author tries to write very, very compact programs and violates some of the style recommendations that I ask you to follow. So take that with a bit of a grain of salt, that these programs are sometimes harder to read, and I wish the author would have used a better style of programming. But the explanations for data structures and algorithms, they are very good, and I'm going to follow them in this course. If you need some additional material to learn programming in C, then I can highly recommend this book. It's a very small volume. It's a very nice introduction into programming, problem solving, and abstraction with C. It is not absolutely necessary for you to have these textbooks if you are happy with the slides, and the way I put them on the website also allows you to print them. There's a nicer format where there are two slides, two sets of slides on one single page as a PDF that you can download and print. Instead of printing these individual slides here, obviously this is not a good idea. Everything that you will need to know is on these slides. So as I said, you don't necessarily have to have these textbooks, but they might prove a valuable addition to all the material that I'm providing. Now with lectures, as you would expect, lectures present theory. I will demonstrate problem-solving methods, sometimes with the help of my laptop here, sometimes also with the help of the document camera. I will demonstrate problem-solving methods and give some practical demonstrations. The lectures do provide an alternative view to the textbook, so it's not just that I'm reading the textbook. I will always, as you have seen, make lecture slides available before the lecture. Typically, I will do that a day before. So if you check on Monday afternoon, then you will always find the slides for the Tuesday lecture there. Do feel free to ask questions during the lecture. This is what you're here for, not just to listen, but also to ask questions whenever you have one. No idle chatting, because we have to get through the material, but I'm always very happy to stop and answer any questions that you might have. We will have weekly problem sets, the first of which you can access on the web page for this week as well. This weekly homework aims to clarify any questions, issues with the lecture material. It will work through exercises that are related to the lecture topics, and in particular give you practice with algorithm design skills. As programs become larger that you have to deal with, it will be a good idea for you to not just jump at your computer and start programming, but to use pen and paper to design and to think before you start coding, to design your data structure, to design your program, and only then to start coding. Problem sets will always be available on the web at the time of the lecture. I typically aim to provide them, put them online on Monday just as well. You don't have to submit anything for this problem set, so it's entirely up to you how much you do of this problem set, though I can very, very highly recommend you to each and every week go through every single exercise and try as best as you can to solve these exercises, because that is the only way for you to make sure that you have understood everything that I have talked about, and also that you're able to apply it to solve your own problems. There will always be, I should add that, not always, but in some of the problem sets, I will have one last exercise that is labeled as challenge exercise. This is meant for everyone who thinks that the normal standard exercises are a little too easy. These challenge exercises are really meant to challenge you. You don't obviously have to be able to solve them to pass this course or even to obtain a high grade. I would rather suspect that everyone who is able to do most, if not all, of the challenge exercises, that they will be competing for the first spot in this class. So it might really be a challenge for you to try to solve them. Sample solutions will be posted in the following week. Of course, if your program looks different but achieves the same thing as the program that I will post, then there's nothing wrong with that. It will really be a sample solution only. To stress my point, do them yourself, do them every week, and don't fall behind. In particular, for the first 3 weeks, if you haven't programmed in C, it is almost mandatory that you do all these exercises so that you will be able to handle the first programming assignment that will be released in week 4. That's problem sets. The assignments give you experience in applying the tools and techniques that we learn about, just like the homework but to a much larger, or I should say a larger programming problem than typically the homework. Both assignments will be carried out individually, and do take note that both assignments will have a Monday 1 minute before midnight deadline. Do note that there is a 15% penalty that will be applied to the maximum mark for every 24 hours late after the deadline. So it doesn't really make a difference whether you're 2 hours late or 23 hours late. This will always count as 1 day, and 15% will be applied to the maximum mark. That is, if you're between 1 minute and 23 hours and 59 minutes late, then your mark is capped to 85% of the maximum possible mark, and this counts down to 0. The two assignments contribute, the first one 10% and the second one 15% to your overall mark. My advice on assignments is that they always invariably take longer than you expect. So you should never leave them to the last minute. Do go to the help lab. The help lab is also there for you to not solve the assignment for you, obviously, but also to help you if you run into problems with the assignment. Don't leave them to the last minute and organize your time, which then means that you we don't have to apply late penalty. If, however, you do leave them to the last minute, the preference for you should be to take the late penalty rather than copying. And that's got to do with the fact that we get very, very annoyed by people who plagiarize. You should just not do it for the assignments, and I'm known for checking that very seriously. Just to stress and reiterate this point, examples of plagiarisms, and this is taken from our web page, West University. Copying is an example of plagiarism if you use a same or a similar idea without acknowledging the source. This includes copying ideas from a website and internet. And it really means not only just the same code as someone else, but also similar code without acknowledging the source. What's also not allowed is collusion. Collusion occurs when you present work as independent, when it has been produced in collusion with others. And what is also important to, what I would like to point out is that that collusion includes, by the definition of UNSW's definition of plagiarism, students providing their work to another student. And that does include someone using a public repository to store your files from which then someone else can copy. This would be an example of collusion because you allow other students to copy. So if you want to use a repository for your code, do make absolutely sure that this is not public but private. Plagiarism in this course will be checked for and penalties will apply. The minimum, if it's a very mild form, will be reduced mark for the assignment, and that can go up to 0 marks for the entire course. I've already mentioned the Help Lab, which aims to help you if you have difficulties with the weekly programming exercises at the beginning, but also with the assignments. And sometimes, if you wish, you can also discuss some of the non-programming exercises from the weekly problem sets. As I said, it will, the Help Lab be offered on Fridays from 1 to 3 p.m. in the computer lab that is called Clavier. It's the lower ground 20, building K14. It's a bit hard to find. The best way to find this lab is to walk past building J14, also because there's a big sign that says CSE Computer Labs that points you in the right direction. Attendance is entirely voluntary, so certainly if you don't have problems with the weekly homework, you don't have to come to these help labs. The midterm test. This will be a 1-hour online test in week 8, and as I said, you can do it at your own time between Monday, week 8, 12 noon, and Tuesday, week 8, 12 noon. And it means, of course, as we get closer, I will reiterate this point and show you how to answer questions on this online test. But just to point out, it means 1 hour, you get 1 hour to answer all the questions. And if the deadline is 12 noon on Tuesday, you better start at 11, the latest, because the test will then close at 12 noon. The format will be some multiple choice questions with possibly multiple answers, as well as some descriptive and analytical questions with open answers. The midterm test will contribute 15% to the overall mark. And then the last component will be the final exam, a 2-hour, not torture, but a written exam during the exam period. It will be similar to the Comp 9020 exam in the sense that it will all be written. If you have attended my course last semester, it will not be like the 9021. It will not be a programming exam. It will be a purely written exam. How will you be able to pass the midterm test and the final exam? I think probably the most important recommendation would be, again, for you to do the homework yourself and to do the homework every week. If you do that and you feel comfortable with the majority of the questions and you feel you're able to answer them without looking at the solutions first, then I can assure you that you will have no problems passing the midterm test as well as the final exam. You should also do the assignment yourself, because by writing these larger programs you will learn a lot about C programming, and there might be some C programming, simple C programming languages in the final exam as well as in the midterm as well. Other than that, it might be a good idea to practice programming outside classes, invent your own problems and write your own C programs, or ask your friends whether they want anything computed and then write your C program to compute, to solve other problems besides those that we look at. You should read the lecture notes, just go through the slides again, and possibly, if you still have questions, read the corresponding chapters in the textbook. So here's a summary of the assessment. We have 2 assignments. The maximum is 10 and 15, respectively. The midterm test, 15, and then that leaves 60 for the final. Your total score will be the sum of these 4 components under one condition, and the one condition is that your mark for the final exam has to be at least 25 out of 60. Otherwise, your total will just be determined by the exam mark, and this will be computed by adjusting it from 60 to 100. But obviously, if you score below 25, then when you adjust this, you will obtain a mark that is below 50. So in order to pass the course, you must achieve 2 things: at least 25 out of 60 for the final exam, and at least 50 out of 100 for total, because that will then be your final mark. Any questions? Yes.
Last semester in 9021, the weekly questions were very, very close to the midterm and final exam questions. There were basically slight variations on them. How close will the questions be to the exam?
Well, that is a bit hard for me to say. I would think that probably at least some of the questions in the weekly questions, because you've got much more time to do them, will be much harder than what you can expect in the midterm and the final. This definitely applies to the challenge exercise, but it would also apply to some of the other exercises. Other than that, I will give you a sample or 2 prac paper so that you get a better feeling of what questions to expect. Any other questions? If you're sitting there in the back, there are still some empty seats here if you want to come forward. But you don't have to, of course, if you feel comfortable in the back. Okay, so to summarize this introduction to the course, the goal is for you to become a better computer scientist, more confident in your ability to choose data structures, more confident in your ability to develop algorithms. You will also be, the goal at least, is for you to be able to analyze your choices and to justify your choices, to give arguments why this data structure is the best possible way for the intended use of the data, or why this algorithm is the most efficient algorithm that computes a solution to a given problem. Ultimately, this should lead to you being able to produce a better end product, and very hopefully also that you will enjoy the program design process, the whole process of developing a data structure, choosing a data structure, implementing a data structure with algorithms, and ultimately solving a problem. With this, let me move on to the first real chapter in this course, a very quick introduction to the C programming language for everyone who hasn't programmed in C before, which I assume is the majority. Can everyone raise their hand if they have programmed in C before? Okay, thank you. Yeah, so it looks like maybe 10%. Which is what is to be expected. You will be proficient in C in no time, I can assure you of that. Well, the first question that I would like to answer is, why are we going to use C? C is a good example of an imperative language. C, and this is now a main difference to Python, gives the programmer greater control. And giving the programmer greater control means that you will learn a lot more about the internal workings of a computer program when you program in C. Sometimes this makes it harder to solve a problem because Python takes some burden off the programmer. But on the other hand, as I said, you will learn more about the internal workings of a computer program. This has two advantages. The first one is that C tends to produce very fast, very efficient code. And secondly, I think it's justified to say that when you know how to program in C, it will be very easy for you to learn any other language. And this is not necessarily the case with higher level languages like Python. But once you know how to program in C, you should have no problems switching to other languages. There are many libraries and resources available for C, including online resources, and C is widely used in industry and in science, and in particular in engineering, I should add. A few words about the history. C and the Unix operating system, they share a complex history. You can't, or it isn't possible to imagine one without the other, because C was originally designed for the operating system Unix, and it was implemented on Unix. C was invented in the early 70s. Dennis Ritchie was the author of C, and then in 1973, the operating system Unix was entirely rewritten in that programming language, C. Why C? Well, C was actually the successor of a programming language called B. The author is Ken Thompson in 1970, and Ritchie and Thompson are typically called the inventors or the fathers of C. Now, the language B was the predecessor to C, but funnily enough, there was never a programming language A. So that explanation stops where we can say C was the successor of B. Now, B was, like Python, a typeless language, whereas C is a typed language. What that means, we will see when we look at our first C programs. It basically means that you as a programmer have to tell the system, whenever you use a variable, what type that variable should be, and whenever you define parameters for a function and a return value for a function, what the types of the parameters are and what the type of the return value for the function is. In 1983, and that was a big development, the American National Standards Institute, ANSI, established a committee to clean up and standardize the language. And there have been several standards defined. The most important was the 1988 published, the first standard, because this greatly improved the source code portability. Now everyone was following with their C programs this particular standard, and that meant that you can take a C program that was developed on one computer and you could compile it on another computer. The second most important standard, I think, was in 99, and it's still being used a lot, but the current standard is C11, and it's called C11 because it was published in 2011. C was and still is the main language for writing operating systems and compilers, and as I said, it is used for a variety of applications as well. Now, let's have a look at the basic structure of a C program. This is how a C program will be structured, should be structured. You, at the beginning, have files to be included and some global definitions, and we will see an example just on the next slide. Then you have different functions that you define, function definitions. You have to say what type that function has, that is, what value does it return? Does it return an integer value, for example, or does it return a floating point number? And you have to say what arguments it takes, and then you define the function that typically ends with a return statement that then returns a value that is being computed. And so you have a collection of functions at the beginning of your program, and your program always has to end in a main function. This will then be the point where, when this program is executed, the execution will start. The main function can also take arguments, and we will see what the arguments of a main function could be. And you have a body of the main function as well. You typically also have a return statement for the main function, and I will tell you in a minute or two what the purpose of that is. So that's the general structure. Let's have a look at one simple example. This is a complete C program. It starts with a very strange statement that includes a particular library file, which is very important because it's very basic. stdio, or standard IO, stands for the library that contains all the standard input and output functions. And this program needs one because it prints a statement. Then I'm defining a function here. You can see that I've provided the system with the information that this function should return an integer, and it takes 2 integer arguments. Then it does some computation with the help of a loop and a conditional, and it returns a particular value. That's the definition of this function. And then I've got a main function that has a funny-looking print statement. We will see it, take a closer look at these print statements later, and computes the function value for the arguments 30 and 18. What you can see is also very typical for C is that blocks of statements are enclosed in these curly brackets. So the, I'm not sure if one can see, here. So this is the opening curly bracket for the body of this function, and this is the closing curly bracket. So everything inside belongs to that function, and you have the same curly brackets around statements inside of the while loop, which begins here and ends here. Now, looking at this statement, what do you think is going to be the output of this function when you apply it to 30 and 18? What is the result? Yes, it computes the greatest common divisor. That's correct. So the output would be 6. Yes, the output is 6. And you can actually go through this while loop and the conditional to see that if you start with m equals 30 and n equals 18, then m is not the same as n. You see that m is greater than n, 30 is greater than 18, so you subtract 18 from 30, which results in 12. That's the new value for m in that if statement. So you replace the 30 by 12, and then you have values 12 and 18. Now, 12 is not greater than 18, so you go to the else part, and you subtract 12 from 18, which gives you 6. So that you now have m is 12, n is 6. Then you subtract 6 from 12. This gives you your new m, and then m and n have the same values, 6 and 6. And then the loop terminates, and it returns the value of one of these two variables, which is 6. And indeed, you're right, this is one way of computing the greatest common divisor of two variables. Now, here's another example. This is using pseudocode, not actual programming code, but a high-level description of a particular algorithm. We will be using, although this course is based on the C programming language, we will be using pseudocode a lot for most of the algorithms that we will look at. This here describes the insertion sort algorithm, of which I assume that you have seen it in 9021. Is that true? Have you looked at sorting algorithms? Yes? No? No sorting algorithms in 9021? Yes, you did. And did you look at insertion sort? Let me illustrate this algorithm with the help of some playing cards. Right. So suppose we want to apply this algorithm to sort these 5 elements. And what you can see if you look at the pseudocode for this algorithm, you see it takes as input an array of numbers. Well, in our case, we have these 5 numbers. We can decide what we do with the A's. Let's count it as 1 so that it will end up as the smallest card. And then what the algorithm does is, you can see the array starts at index 0 in this algorithm, and the for loop starts at index 1. So we don't start with the leftmost. This would be our array 0 here. We start with array 1. And then we go 2, 3, and 4. This is the outer for loop. And then inside of the for loop, it says we have to take the ith element. This is our element here, element in the first step. And now it says that we start at index j, which is I minus 1. In our case, this would be 0. I is 1. This is 0. I might even add that here. So that's the index. We start with j equals 0, while j is greater or equal to 0. And the card that we find in aj is greater than the element. We move that card up 1 position, from j to j plus 1. So if we look at aj, which is a0, number 10, this is actually greater than our element, because we wanted to count this as 1. And that means we move this up to here. Well, as a matter of fact, what it does is it copies the value from a0 into a1. But this will later be overwritten So let me just move this card here. And then the loop ends because j is reduced from 0 to -1. And then, of course, -1 is no longer greater or equal to 0. So the while loop ends. And then after j has been reduced to -1, aj plus 1, which is a0, will get the element. And element was this a here. So this would be moved upwards. This is what happens in the first step of the for loop. And this now continues. I'm moving, this was the first I equals 1 that I had in the first iteration of the loop. Now I'm looking at the second element, 9. I take this as my element. And I do the same thing as before. I start at I minus 1 and compare all the cards that I find here until I reach the point where aj is no longer greater than the element that I've got here. Now 10 is greater than 9, so I'm moving it. Ace is not greater than 9, so I stop with that while loop and I insert that card here. What happens with 7, the next iteration of the for loop? 10 is greater than 7, 9 is also greater than 7, ace not greater than 7, while loop terminates, and 7 is plugged in here. Last iteration for the for loop. Card number 8, 10 is greater than 8, 9 still greater than 8, 7 not greater than 8, while loop stops, and 8 is inserted here. So this insertion sort is named insertion sort because every card is inserted as we move from left to right into the right position. And if you have followed closely what I've been doing, then all the cards to the left were always correctly sorted. And then I've taken the next card and I just try to find the right place to insert it into this list. And you can see that the cards are now being sorted according to this algorithm. So that's the insertion sort algorithm. It uses this outer for loop and the inner while loop. And let's now have a look at how we would encode this in C. And let me go through this program in a little more detail because this is now the first real C program for you to see. And right after that, we will have a short break. Now, this program begins with the same so-called hash include statement as before. I'm including a standard library. Again, the standard I/O library. That allows me to use all the standard input-output functions in my program. Then I'm using another global definition, so-called hash define definition, which defines a constant called size here to have a specific value 6. And the effect of doing this is that wherever in the program this string size occurs, it will be replaced by 6. It's actually a very good programming style to define these symbolic constants, and I will, a little later in the second part of today's lecture, illustrate and explain why it does make sense to define these symbolic constants for readability, as well as if you want to maintain your program. Now, I have one big function which does the insertion sort. This insertion sort is supposed to sort all the cards. It doesn't have to return anything, and this is why the return value or the return type of this function is defined as void. That means it doesn't return a value at all. It is more like a procedure rather than a function that returns a computed value. Now, this function takes 2 arguments. It takes an array of integers to be sorted, and it takes a number n, which indicates the size of the array, how many elements are in this array that need to be sorted. Then the rest of this is mostly an implementation of the actual algorithm that we have seen on the previous slide with that outer for loop and the inner while loop. Let me just illustrate a few aspects of the syntax. I have to declare a variable before I can use it. Here I'm using that index variable I, and I'm also using that index variable j, and you can see I'm defining I as an int, and later on I'm defining j as an int. I'm also defining element as an int. The syntax for the for loop looks a bit funny, but this is how you do that in C. For I equals 1, up to n and I++ means that I is incremented by 1. The syntax for a for loop, unlike in Python, makes it very, very clear to which point you have to iterate. You iterate the loop until I is no longer smaller than 1. So it really is a loop for I equals 1 to n minus 1 inclusive, but not n. Then the element is said to be the ith element of the array, and I have a while loop whose condition consists of two parts. J must be greater or equal to 0, and the jth element of the array must be greater than the element. This double ampersand is the sign for logical AND in C. Then in the while loop, I'm just copying the two statements that we had in the pseudocode. Array j plus 1 equals array j, and j is decremented. J equals j minus 1, which in C can be written with the shorthand form j minus minus. And at the end of that while loop, the element is assigned to array j plus 1. This was the insertion step of that card. Then at the end, you can see here's the main function. I'm defining a particular example of an array that I want to sort. It contains 6 elements, and I'm applying or calling the insertion sort function that I've defined earlier without a return type. And then here I'm using a for loop to print all the elements in that array. And I, as we will see later when we look at these format strings, make sure that every number is printed on a single individual line. Lastly, the main function here also ends with a return statement, return 0. That does mean that the main function, and with it the whole program, returns the program status to the environment. If you run this program under Unix, for example, the environment that has started this program can use the return value for further processing. And what you typically use it for is to indicate that some error has happened, where by definition 0 means that no error occurred. And this is why normally a main function should end with return 0, just to indicate that everything has been processed normally. Whereas if you have a statement inside of the program that causes the program to abort or terminate prematurely, then you can provide another value different from 0 as the return value that can then be used by the environment. So that's how a typical C program looks like, a function definition and the main program. And I will now have a short break, 7:03, so that we will restart at 10 minutes past 7, and then I will show you how to run this program. All right. folks. Let's continue. Everyone, thank you for, hello. Thank you for listening. Right, so let's continue. One thing that I still wanted to show you is the right-hand side, which you couldn't really see, which also illustrates how you can write comments in your program. You can either use these double slashes, and it explains a bit about the workings of this program. For example, as I said earlier, function headers must provide types. Each variable must have a type. We have seen the syntax here. We have also seen that, you would have seen that every statement is terminated by a semicolon, and that code blocks are enclosed in these curly brackets. If you want to write a program that goes over, a comment that goes over more than one line, you would use this syntax, /* and */, and then you can write a longer comment. The program has been using one standard I/O function, printf, which is defined in that standard I/O library that I've been including at the beginning. Okay, now let's look at how, once you've written a program like this, how you can, and now all of a sudden the mouse seems to be working, how you can run this program. Suppose you have a program, you have given it a name and called it program or prog.c. Now you want to produce something that you can actually run. This is what is known as an executable program. The standard name of an executable program that is being produced when you use a standard compiler is called a.out, but you can rename it if you want. And to obtain this executable program, you would type the following under, for example, the Unix system. GCC for the C compiler, program C, and this will then produce that executable. In order to run that program under Unix, you would say, run this program, a.out, and you have to add the directory name. Even if it's in the directory where you want to execute this program from, you still have to say /a.out to tell the system that this is an executable program that you want to execute from where you currently are. So if, for example, you have written the greatest common divisor program in your favorite editor, I'm using Emacs, but you're very welcome to use your favorite editor to write this program, then it contains everything that it should contain, including the main function. And you can see this is the program that I've got here. I've called it GCD, greatest common divisor of C. And now I'm executing this command here, gcc, gcd.c. And you can see it has produced this executable a.out, which I can now run. And the output, not surprisingly, is 6, because this is the value that is being computed. I've also implemented the insertion sort. And before I do that and run it, let me show you a few more options that you have when you compile a program. First of all, note that when you use the command line compilation on my laptop here or on a CSE computer, a lab computer, then the default would be that it doesn't give you any warnings about potential problems. And that in itself can be a potential problem, because you can very often compile a C program that is syntactically correct, but where it's very likely that you have a typo in there nonetheless, so that the program, when it's being executed, would do something that you would find, or that is very unexpected. You can add an argument to the command line compilation. That really is very good practice, and even I still do it just to be sure that I will always be warned about any errors or warnings that can be generated. To be tough on yourself and to say, I want to generate all possible or get all possible warnings and errors, which does report all warnings to anything that it finds that is not necessarily wrong, but potentially wrong and not compliant with the standard. This is one thing, and the second thing is if you don't like the name a.out, and typically you won't, also because it would always produce the same name and overwrite your previous program, you can use the command line option -o to give the output a name. And I would really appreciate it if you could stop talking. If you have any questions, just ask. So you can give it your own name. And let me do that with our insertion sort program. So that's the insertion sort with the hash include, the hash define, the main function, the insertion sort, and the actual main function called main with that particular same array, and the for loop that in the end outputs all the numbers in the array starting from left to right in the single line, and hopefully the output then will be 1, 2, 3, 4, 5, 6 to see that the numbers have really been sorted. Now I can compile it with the requirement to show me every potential warning or errors. Now hopefully there aren't any in this particular program. And -o, I can give it a name, and I can, for example, call it ins sort. Ins sort.c. So that now produces a program that is called ins sort, and it compiles the program ins sort c. And you can see it has created that file here, which is now also an executable. And when I run it, it does indeed produce the expected output. The numbers have been sorted. A little warning, when you use that command line, it's sometimes easy to write something like this. But that means that you're giving the output the same name as the input. And what would actually happen if I run this command is that the C program that I've just written will be overwritten by its own executable. This is probably not what you want, in particular if you don't have a copy of that program. It would be lost if you do this. All right, so this is how we can basically compile a C program and get a program to run. Now, the homework for this week asks you a few simple exercises to solve fairly simple problems that I'm sure you would be able to solve in Python after you've successfully gone through 9.0.1. And the challenge here now is really to get used to the C programming language and to write the same algorithm now in C and see if you can compile it either at home or at one of our computers in our computer labs. By the way, if you're working from home, then on the web page I've given links to some web pages that explain in detail how under different systems, like on a Mac or on a Unix or a Windows machine, how you can access the computers that we have here at the university remotely. And for example, test programs with the tests that I provide for the homework, even if you work remotely, and also submit assignments and make sure that they compile on the machines that we have here, which is one requirement for the assignments. Okay, so now we can start looking at two things for the remainder of today's introduction. We look at how to write basic algorithms in C and how to use basic data types and build basic data structures in C. Let's start with algorithms in C and just have a look at the individual components that go into algorithms. As I'm sure you know, basic elements for algorithms are assignments. Values are being assigned to variables. You have conditionals, if then else's. You have loops like while and for loops, and you have function calls and return statements. With regard to assignments, in C, first of all, each statement is terminated by a semicolon, without exception. Curly brackets, as we have seen, are used to enclose statements in a block. And then you can use in C the usual arithmetic operators, and they are exactly the same as in Python. Addition, subtraction, multiplication, division, integer division, and modulo division to compute the remainder. You have the usual assignment operations. The simplest one would be equal. X equals 3 would assign the value 3 to variable x. You can also use these compound assignment operations that are also available in Python. Plus equal, for example, means if you say x plus equal 3, that abbreviates x equals x plus 3. So it will add 3 to the value of x instead of just assigning 3 to x. And you can do that with all the other arithmetic operations as well. Then a specialty of C is that you can use the operators double plus and double minus to increment a variable, that is to add 1 to an integer variable, or to decrement the variable, to subtract 1. There is actually two different ways in which you can use it. The recommended one would be to use it in the way that we have seen earlier, namely to put the increment or decrement operator after the variable. You can actually put it in front of the variable as well. Let's see what the difference might be. Suppose we have a variable k, and k has value 6 initially. And then you've got a statement k plus plus, which means to increment k. Afterwards, obviously, if k was 6, then you expect k to be 7. You can also combine this increment or decrement operator with an assignment. And what would happen here in this case is, if you say n equals k minus minus, that combines two statements in one. It says assign k to n, and then decrement k by 1. If you do that, remember that k was now 7, then afterwards n will be 7, and k will have been reduced to 6 through that decrement operator here. You can also use, as I said, the increment and decrement in front of the variable, and that has a different effect when you use it in a combined statement. It doesn't make a difference when you have it as a single statement. Plus plus k will just be the same as k plus plus. It will increment k by 1. But the difference would then be in this assignment here. Because since the minus minus is now in front of k, it means that k is first decremented, and then the result is assigned to n. So here, if k has the value 7, it will get the value 6 first, and then the value 6 will be assigned to n. That is the difference between k minus minus and minus minus k. My recommendation would be to never use this, and maybe to even avoid that. It is just much clearer for anyone else who reads your program if you say n equals k, and then you say k minus minus, because that also means you won't make a mistake. And maybe you intended to decrement k first, and instead wrote k minus minus. If you separate these two statements, then it will be very clear for everyone who reads your program, but it will even make your life easier when you go back to your program a few days later. You see these two statements, you know exactly what you intended to express with these two statements, whereas when you try to be too compact, sometimes it might just make your own life harder. Right, let's see what else we have we can say about assignments. As a matter of fact, every assignment statement, when you say x equals 3, for example, this is really an expression in itself. And as an expression, it can return a result, or it does return a result, which is actually the value that is being assigned. Now, this return value of the assignment is generally ignored. If you have a statement in your program that says x equals 3, then 3 is assigned to x, and the value of that statement is 3. But this 3 will be ignored. No one is going to use it if you use it as just a standalone statement. But frequently, assignments are used in loop continuation tests, for example, and then it becomes important that every assignment has its own value, because that allows you to combine the test with collecting the next value and to make the expression of such loops more concise. Let's have a look at one example. Suppose we have a very standard loop, whatever exactly get next item does, doesn't really matter. You just get the next item v, and you say that as long as the value v is not 0, you do something with that value v, and then you get the next item. Well, that's a very standard loop, as you can imagine. This in C is very often written in a much nicer, more compact form, where you combine the assignment to get the next item with the condition in the loop to check it. So here you assign the next item to variable v as before, and after you've been doing this, you immediately check whether this new value is satisfying the condition or not. And here you see why the assignment, or where the value of an assignment is being used. The value of that assignment is the value itself that is being assigned. So it would be the next item. And therefore, you can use that expression to immediately test against that condition. If you find that confusing, don't use it. But after a while, I think you do get used to the idea that assignments themselves always have a value and that you can use them in conditions. And you will see me using that in later parts of this course as well. Well, let's see if you have understood what I just told you about the increment and decrement operator in particular. Let's look at the first program, a equals 1, b equals 5. And I've got a loop while a is smaller than b, increment a and decrement b. What is the final value of a and b at the end of this loop? What's a, what's b? 3? Both of them? Both of them, yes. Both will be 3 in the end. At the beginning, 1 is smaller than 5, and then a becomes 2, b becomes 4. Still 2 is smaller than 4, and then you increment and decrement a and b respectively again, so that they will end up both being 3, and then they don't satisfy this condition anymore. All right, a bit more challenging. What about the second program? What will be the final value for a and b? Five and 3? 5 and 4? Any other suggestion? 3 and 4? Okay, so we've got 5 and 4, 5 and 3, 3 and 4. Okay, let's see. The correct solution was among the suggestions that you had. It's actually 5 and 4. You have to take into account that when you do this assignment, that it is actually being carried out before you check it. So let's see what happens in the first step. A equals 1, then A is incremented by 2. So A is 3, and this is still smaller than B. So 3 is smaller than 5, and that means 5B is decremented to 4. So you've got 3 and 4. And now in the next step, you add 2 to A, which becomes 5. So A becomes 5. Remember, B is now 4, and 5 is smaller than 4. That is the while loop. 5 is not smaller than 4, and this is why the while loop ends after just one round. And we then have that A has been incremented twice by 2, so that it ends up being 5, and B has been decremented once because we went through the loop once. Is that clear? Does that make sense? Good. Of course, if you don't believe it, you can always implement this and test it for yourself. So 3, 3 in the first case, 5, 4 in the second case. All right, so that was assignments. Now, conditionals. We have two types. A bit like in Python, where you have the if and you have the if and else if. Here we have the if expression, and then in curly brackets, some statements. Or you use the else, if expression, some statements, 1, else, some other statements, 2. Now what happens here is, in the case of just a simple if, the expression is being evaluated, and if and only if the evaluation of the expression returns non-zero, then some statements are being executed. So we evaluate an expression that can return an arbitrary value, and if it is not 0, then this is interpreted as true, and the statements are being executed. In the second case, again, if expression returns a non-zero value, then some statements 1 are executed, otherwise some statements 2 are executed. Statements themselves, they can be single instructions, in which case you don't necessarily have to use these curly brackets. But as soon as there's more than one statement, you have to use curly brackets to make sure that all these statements are only executed in the else case. Now with if statements, we can already see that what is known as indentation, that this is very, very important in promoting the readability of the code. In Python, as you know, you have to use indentation. This is how the system knows which statements belong to which block. In C, we use curly brackets, so you don't have to use indentation, but it is mandatory for readability that you follow your own style of indentation. And the standard would be to use 3 spaces or 4 spaces. You can choose either of the two, but make sure that you're consistent. For if statements, there are 2 styles that people generally follow. One is shown here. The other one, slightly more compact, is to put the curly bracket right behind the condition. And I generally prefer this. Although when you look at other people's programs, you will frequently see this style where the opening curly bracket is always put in a new line. The preferred else-if style, in particular if you have more than one else statement followed by an immediate if statement, is this compact form, where you say if expression, else if another expression, else if a third expression. In this form, this is nice and compact and very readable because you can visually see, you can see exactly which statements belong to which block. As for the conditions, we have the usual relational and logical operators, like greater, greater, equal, smaller than, and so on. Also not equal, exclamation mark, equal sign, just as in Python. What is different to Python is the syntax for logical AND, which we've already seen in our insertion sort example, and logical OR and logical NOT. You use the double ampersand, the double bar for logical OR, and the exclamation mark. And make sure that you always use double ampersand and double vertical bar, because if you use only a single ampersand, this is a different operation that we might see later. Normally with conditions in if expressions, you always want to express logical AND and logical ORs, so you should always double on these symbols. Now if you have a relational expression or a logical expression, then that evaluates to the value 1 if the expression is true, and it evaluates to 0 if it is false. So if you have an expression 3 greater than 4, this expression itself has a value 0 because 3 is not greater than 4. And we have seen on the previous slide with the conditionals that if expression, then statements, means that the statements are executed when your expression evaluates to a non-zero value. And obviously 1 is a non-zero value. So this means that if it evaluates to true, then you would observe the expected behavior in a conditional. So that's important to know. Let's see yet another example, or rather 2 examples. Look at the first program. This combines logical operations and standard relational operations to 2 variables x and y, and it prints yes in one case and no in the other case. What do you think is going to be the output of the program? Oh, you may ask, doesn't that depend on x and y? Well, do think about it and think what the result will always be. Anyone? No. It will always say no. Yes, that's right. And the reason is that the condition here, the combined condition, will always be false. You can't have that at the same time x is greater than y, and it is not the case that y minus x is smaller or equal to 0. This is logically impossible. So it's either the first or the second that is false. And if one of the 2 are false, then the logical AND means that they are definitely false. If you still don't believe it, just try a few examples. 4 is greater than 3, but 3 minus 4 is indeed smaller or equal to 0. So not true will then be false, and then you have true and false. So the output will always be that it goes to the else part and prints nay. What about the second statement? What is the resulting value of x, the variable x, after the following assignment? It is always 1. Yes, that is correct. Remember that every relational expression does have a value. So x greater or equal to 0 is either true or false, and therefore this in itself has a value 0 or 1. And this also has a value 0 or 1. And in fact, if one is false, the other is true, and vice versa. So you always add 0 and 1. And if you assign this value then to x, it means the resulting value for x is 1. Very good. So that's the answer. The condition is unsatisfiable, hence the output will always be the else part. And as I said, one part of the sum will be 1 and the other will be 0. Therefore, x will be 1. Now, a side track. we've already seen how to print values, well, we have seen examples of how to output values with the help of the printf statement. Printf has the effect that it outputs its argument to the standard output, which by definition, unless you define it differently, is the screen. As we have seen with the program when I ran it on my laptop, the output in both cases was just printed on the screen in the shell where I was running it. The general syntax for printf is that you start with a format string to tell the system how the output should be displayed. And then you can have one or more expressions to print. Now, the format string uses the following placeholders. If you want to print a decimal number, you would say %d. If you want to print a character, %C. A fixed point real number, and %S for strings. You can also use the \n for new line, so that the output, the next output then starts on a new line. This is what I've been using in the program where I output the result of sorting. Every number was output with, see if I can find it. That placeholder %d. So it outputs the number itself, numbers I, and then it ends with that \n, so that it means the next output will happen on the next line. We were somewhere here. So just a few other examples. Here we have a variable num, which is obviously an integer, has been defined as an integer before. And then I want to say that the cube of a number is another number. And I want to put that, or the next output should start in a new line. Then I can use this format string here. It contains exactly 2 placeholders, as you can see here. And the 2 placeholders should be replaced by the value of the variable num, first one, and the second one by the result of the expression num multiplied with itself twice. So that in this particular example, the output then will be that these 2 expressions are being calculated and being inserted into these placeholders, so that you see the cube of 3 is 27. Another example, I'm using a character that I've defined as a character, this variable ID before, character Z. Then I've got a number 1, 2, 3, 4, 5, 6, 7, and I'm outputting this string with the help of 2 placeholders. And it uses this so-called escape sequence, which has been defined here. This is how you can display the quotation mark itself. This is necessary because the format string itself is enclosed in quotation marks, as you can see here. So if you were just to put the quotation mark in here, then the C program would think that your string just ends at this point, or actually it would end at this point at the first quotation mark. But with the / quotation, it means this is an actual character inside of the string. And this is why the output then will look like this. You have that character Z, and immediately followed by the number, the value of this variable num, which was the 3rd argument here. Lastly, you can also use width and precision. If you want to tell the system that it has to use a specific format for a floating point number, then this format string here says %8, use in total 8 spaces, to output the result and output the result to a precision of 3 decimal points. So if we have the value 3.14159, it will be rounded to 3.142, which is the 3rd decimal point. It will be rounded. And you can see that there are a few spaces at the beginning of this output due to the fact that I've told the system the whole string, the whole output should take 8 spaces. Is that, sorry, what? What actually happens is when it's being sent to the output, the entire thing is sent as a string to the output. So if you have another program that then reads output that has been printed on the screen, it would actually interpret this as an entire string, not as a number anymore. Okay, so that was conditionals, and as a sidetrack, how to print numbers. Let's now look at the 2 types of loops, while and for loops. They're actually, and again, I would appreciate it if you all would stop talking while I'm talking. Everyone, please. C has 2 different ways to use a while loop. The first one is probably the more common, while an expression some statements. We can also use a so-called do-while loop, where you start with the keyword do and then have while expression at the end. The only difference between these 2 is that the second syntax ensures, because it doesn't even have a test at the beginning here, that the loop is executed at least once before you check this condition. Whereas here you might have that the expression is false right from the start, and that would mean that the loop is not executed at all. That's the while loop. I think this is pretty straightforward. Do notice that, just like with the if conditions, when you have an expression, in an if as well as in a while, you have to enclose the expression in these brackets, opening bracket and closing bracket. So even if that is a simple statement like x greater 3, you have to write while, open parentheses, x greater 3, closing parentheses. Now, the for loop does have a bit of a funny syntax. That, however, is being used because it allows really great flexibility. The general syntax for a for loop is this. You have the keyword for, and then there are 3 expressions, expression 1, expression 2, and expression 3. And they serve their own purpose. Expression 1 is an expression that is being evaluated before the loop starts. And only once, and then never again. This is typically being used to initialize a running variable. For I equals 1, this will be an expression that is being evaluated. The running variable I is assigned the value 1 at the start of the loop. And then it will never be looked at again. Expression 2 is evaluated at the beginning of every iteration through the loop. And the loop is continued if this expression has a non-zero value. And this is typically being used for the terminating condition of the loop. As you can see here, this says that the loop should continue as long as I smaller than 10 has a non-zero value, that is, as long as this is true. And lastly, the third expression, this is one that is being evaluated at the end of every iteration through the loop, and that in the standard form of a for loop is being used to do something to the running variable of the loop. Typically, it would be an increment or a decrement. So this is the most standard way of using a loop. You're starting at 1, you're incrementing I by just 1, and you terminate as soon as you have reached 10. The syntax makes it very clear that 10 is not being included in that loop. 9 will be the last value that this loop runs through. Let's have a look at this program. That makes it a little more interesting because it has 2 nested loops, and it also has a bit of a stranger calculation with the running variable. Look at this program, think about it, and then let me know what you think the output will be. So what do you think is the first 2 numbers that are being printed here? Both 8, yes. So it will print 8 and 8. And then the next output will be on the next line. What comes after 8, 8? 8, 7, yes. Because J also started at 8, and then J is decremented. So the outer variable is still 8. You start with the inner variable 8, and then 7, then 8, 6, 8, 5, 8, 4, until 8, 1. We can actually, it looks like 81 that we get in the end. And that 81 terminates that inner loop. Now that put character new line is another way of outputting to the screen only 1 single character, as the name suggests. It's also defined in the standard libraries, and it means that the next output will not only start in the new line, but there will be an empty line before I'm continuing with the output. What will be after 81? What will be the next number that is being printed? 44, that's right, 44. I is halved from 8 to 4. And this is why the second loop starts also at 4. So we have 44, 43, 42, 41, and then 22 and 21, and nothing else. Because after we have that I is 2, after I 2 is divided by 2, I will be 1, and I only want to continue this loop as long as I is greater than 1. So yes, very good. This is exactly the output that we can expect from this program. It would look like this: 88 down to 81, then a new line or double new line, 44 to 41, and then 22, 21. The last aspect before we move on to the basic data structures and data types in C, the last aspect for the basic elements for algorithms in C are functions. We've already seen that functions have the form. You have to say what return type the function has. Then you give the function a name, and you have parameters. Inside of the function body, you might have declarations, such as declaring variables as being of a specific type. Then, of course, you would expect to have some statements. And in the end, you may have, or you should have, a return statement. If your function does actually have a return type, then at some point you have to return a value. We've seen an example of a function that doesn't actually compute anything in terms of what it should return. This function was just sorting elements in the array. And I've given this function the return type void, which means that the function does not return a value at all. On the other hand, you might have functions that don't need any parameters at all, in which case you would also use this keyword void instead of listing all these parameters. What happens when a function is being called is memory is allocated for the parameters and the local variables that occur in a function. This only happens when you call a function. And we will be looking at this in more detail later in this course. The parameter expressions in the calling function are evaluated. So you look at what parameters this function gets. C uses call by value parameter parsing. That is, the function works only on its own local copies of the parameters, not the ones in the calling function. So if you have your function called fmn, and these are the parameters, m and n, and somewhere in the main function, for instance, you have variables x and y, and then you call the function by saying f of x and y, then x and y are being evaluated, and the values of x and y are being given to your function, and they will be assigned to the parameters m and n. And then the system will work with these local variables and compute something, but it will not change anything about x and y in your main program. You have to make sure that local variables are assigned a value before they are being used. Without assigning a value, they might carry random numbers or so-called garbage. And if that happens, then you can't predict what your program is doing. The function code is being executed until the first return statement is reached. And when the first return statement is reached, the expression is evaluated, and the function returns to wherever it has been called from. So the function terminates. If you have a return expression, then the expression will be evaluated and will be returned as the value of that function. All local variables and parameters will be thrown away when the function terminates, and the memory that has been occupied by these variables can be reused by other functions. The calling function is free to use the returned value, or it can ignore it. Here is another implementation of the greatest common divisor, or another way of computing the greatest common divisor using Euclid's algorithm that instead of subtraction uses the modulo division. And this definition here uses recursion. So we've got a function Euclid greatest common divisor with two parameters, two integers m and n. And it says that if n is 0, then you return m. Else you return whatever from a recursive call of that function you compute for these two numbers n and m modulo n. That is also known to compute the greatest common divisor. So if you start that with the same two numbers that I had earlier, which was 18, and I forgot what the other one was, but yes, thank you. The result would also be 6, as the greatest common divisor of 18 and 30 is 6. And you see what happens here. Euclid GCD has been defined as returning an integer, and whatever is being calculated here recursively is the result that then is again being returned by the previous call of that function. If you have a function that does not return anything, then you can also use the return statement without an argument. You can just say return semicolon, and that would mean that your function, which doesn't return a value, would terminate at this point. Normally, functions would terminate when they've just reached the end of the function body, but you can also terminate a function prematurely. Like this one here, when you say return m, obviously there's nothing else that is being executed, even if there were other statements later in this function. Returning always means to terminate a function. I think that is really perfect on time. The last bit for today's introduction to C will be to look at basic data types and basic data structures in C. And I suggest we have another 10-minute break before I will do that. Okay, folks, last 50 minutes, or even a little less, to complete the introduction to the C programming language. If I could have everyone's attention, please. Let's look at basic data types and data structures to complete this introduction. As I've said several times in C, each variable must be given a type. There are 4 generic data types. You should be familiar with them from other programming languages, such as Python, except there you don't really have to give every variable a type. We can have single characters. We can have integers, positive and negative ones. We can have floating point numbers, and we can have a so-called double, is the keyword for a double precision floating point number. There are other basic types, but these other basic types are variations on these, and mostly these 4 are the ones that we will be using. Variable declarations must specify a data type and a name. You can, at the same time, with a declaration of a variable, you can initialize a variable. Here I'm declaring x as a floating point number, ch as a character, and I'm immediately initializing it. And you can also initialize variables by assigning the values of other variables, provided, of course, that I itself has a value that has been computed earlier. These are the basic simple types. Let's look at basic aggregate types. There are basically 2 of them. Homogeneous, there is an E missing before the O. But anyway, homogeneous means all elements have the same base type. A standard example is arrays. They can be declared as you have a character array called S, which contains 50 elements, or you have an integer array, V, which contains 100 elements. You can also have heterogeneous aggregate data types, and this will be the very last data structure that we will be looking at in today's lecture. But let's look at the arrays first. An array is a collection of same type variables arranged in the memory of your computer as a linear sequence of elements of the same type. They are accessed using an integer subscript. For an array of size n, do note that valid subscripts are 0 to n minus 1. So if we define an integer array, an array of 20 integer values, a, then valid subscripts would be a0 is the first element up to a19. The number that is being used in here would be the first invalid index. You shouldn't say a20. Character array B has 10 characters, and again they would be accessed starting with B0 for the first element up to B9 for the last element. Here's a slightly larger example. I'm defining a symbolic constant max 20 to indicate the size of the array, and I'm using that symbolic constant several times in that program snippet. What I'm doing here is I have an integer variable I have a factorial fact array up to 20 values, and I'm initializing the first element number 0 with 1, and then I've got a for loop that actually does compute the factorial of the index by multiplying I itself, starting with 1, with the factorial, what I've computed earlier, in I minus 1. And the result will be that fact 0 contains the value 1. Fact 1 would also contain the value 1, and then 2, 3, 4 will always contain the factorial of that number. Now you've seen that I've been using this hash define size. In this case, it was 20. This is known as a symbolic constant. And it is very good programming style to define symbolic constants in your program, and also to do this at the top of the file. Two other random examples are hash define speed of light, and then you give a specific number, or hash define error message as a particular string, which is called out of memory here. The reason for using symbolic constants is that it makes the code easier to understand. Instead of using just random numbers everywhere in your, or seemingly random numbers in your code, you at the very start for yourself as well as any other reader of your program, you make it very clear what this number means, namely the speed of light or the error message. First advantage. Second advantage is if you want to change something, for example, you're using this error message many times in your program, and you want to rewrite it or slightly change it to having an exclamation mark here, for example, then you have to do it only in one place, and you don't have to go through your entire program to make that change. It is customary, every C programmer does this, that symbolic constants use all uppercase letters. And I ask you to do the same thing. That has the advantage that when someone reads your program and they see all uppercase letters, that they assume you follow the same convention, and therefore will just scroll back to the beginning of the program and check what it has been defined as. So do use always uppercase letters, every C programmer does, for these symbolic constants. What happens is that the compiler's preprocessor, before it even starts compiling the code, is it will replace all occurrences of this name here with the replacement text. What it doesn't do is it will not make the replacement if you happen to use the name that you've been using here as part of a string itself. Because if you use that inside of a string, it was probably meant not as a replacement for a symbolic constant, but as an actual string that you wanted to output. With this, I should say that style is really very important for C programs. One of the disadvantages of C, and maybe the only one, maybe the main disadvantage of C, is that you can write code that is totally unreadable. And this is why it is very important to follow a style guide. The School of Computer Science provides a specific C coding style guide, but this is used for bachelor students in their first year. It is not strictly mandatory for this course here, for example, for your assignment, but it's still a good idea if you click on that link and check this style guide. It is a very useful guideline, and it includes, for example, the recommendation or the requirement to use proper layout, including consistent indentation. You should keep functions short and break them into sub-functions as required, and you should always use meaningful names for variables, not just x, 1, 2, 3, 4, but really give us useful names. This is not necessary for index variables. If you have a short loop, then of course you can use I and j and k for these index variables. But other variables, you should always use meaningful names. In particular, style considerations that do matter for your assignments and that will make up part of the mark that you will get for the assignment is to use these symbolic constants to avoid burying just magic numbers that no one can understand inside of your code. You should use indentation consistently. Use either 3 or 4 spaces. Do not use tabs. Some people do that, but that only works well for very, very short algorithms. As soon as you have 3 or 4 nested loops, if you use entire tabs for indentation, the statements inside of 3 or 4 loops, they will just move too far to the right, and it becomes far less readable than using 3 or 4 spaces. Mandatory will also be to add comments to your code to explain what you're doing. The reason why we have these style guides is that C does have a reputation for allowing for very obscure code, which even led to what is known as the International Obfuscated C Code Contest, which is being run every year since 1984, and the goal there is to produce a C program that works and follows correct syntax, but which is totally unreadable. And so that anyone who looks at it would not be able to tell what it does. And then there are prizes for the most obscure code that you can generate. There is a website where you can check some of them with hundreds of examples of bizarre C code. I can assure you that if you're able to understand just half of them, then you would definitely be a C master. Just to give you one example, this is code. Now, I'm not sure whether this is probably the most artistic code that I've ever seen. I'm not sure if you can really see it, but it's a small train that goes from left to right. So, yes, train here, and this is the start. And actually, when you run the code, it outputs something like choo-choo, what every good train should do. So very artistic, but you can be very sure that you will get 0 marks for style if you use that in an assignment. This is rather artistic, but it still is somehow possible to read it, whereas this one is probably the most obscure code that I've ever seen. It just uses this hash define, which I told you replaces one string by another. And this person has even hash redefined the define as O and then produced that code here. And I'm sure this is certainly not possible to understand what this code does. A warning also, it doesn't follow the latest standard anymore because it's a pretty old code. As you can see, it's from 1985. So you can't compile this anymore. Your compiler wouldn't accept this. But at that point, this was valid C code and just illustrates that you can write code that is certainly unreadable. It continues here, but it doesn't really make much of a difference, I would say. All right, back to our arrays. In C, we also have strings, sequences of characters, but string is just a special word for what is internally represented as an array of characters. The end of a string is denoted by a particular character, which can be expressed as escape character or \0, which has the actual value 0, but it is of type character. This is why it's surrounded in these quotes. And this will always be in an array that signifies a string, the last character to be interpreted as the end of a string. So if, as an example, we have an array S that contains 11 characters, and it does express the string hello, which in itself contains 5 characters. This is how it would be stored in memory as an array of characters. The first character at index 0 would be H, and then we have these 5 standard characters. The end of the string will be indicated by the last, or the 5th in this case, the 6th to be precise, index number 5, character to be that \0. And that helps when, for example, you tell the program to print this string. It knows that it prints these 5 letters and then ends the output because it finds the character, the 0 character at the end. You can initialize arrays just like you can initialize any other variables by either code, where you assign values to individual elements, or you can specify an initial set of values in a declaration. You could do that with a string, an array of characters, which would be defined as character, then the name of the array, and the size of the array, 6 elements. And you can assign individual characters to the individual elements of the array in this way. This is a bit clumsy, and this is why you can also, and this would have the exact same effect, you can write or use an actual string included in these double quotes. The result would be that make sure that you reserve at least 6 elements for a 5-letter string so that you have always enough space for the terminating 0 character, which we have here, which is implicit in this string. You can also only partially initialize an array if you have an integer array called fib for, in this case, Fibonacci numbers. 20 numbers, you can just say 1, 1, and this would assign 1 to the first, fib 0, and to the second, fib 1 element of this array. You may even let the compiler decide how many elements this array should have if you leave that open and instead initialize the array. Here we have 5 elements, so the compiler would give you an array of 5 elements. So in the third case, we have initialized only some of the elements, and that does not mean that the initial values for fib2 to fib19 are all 0, but they will have just random numbers and are undefined. And in the last case, as we have seen, C can infer the length of the array. Let's have a look at an example. Again, another exercise for you. Here we have 2 arrays, one integer array and a character array. And then I'm doing something with both arrays. And the question is, what is going to be the output of this program after I've processed these arrays? Look at it briefly, and then maybe you can already see it. If not, then I will take you through it. And in order to do this, I will switch one of the projectors to my document camera here. You can still see the program. Either on the previous slide, if you're listening to this lecture, or if you're sitting in the lecture hall, you can see it on the second projector here. So what happens to these 2 arrays? We've got the integer array initialized as 10, 10, 10, and we've got the string initialized as with the string art. Maybe let's look at the integer array first and see what this loop does with the integer array elements. We've got array 0, 1, and 2. So that's the first thing that you have to keep in mind, that you always start at 0. So when the loop says for I equals 1, it is not the first element that we are dealing with when we assign a new value here for array I. So this is initialized as 10, 10, and 10. And then what happens in the first step of the loop? Which array element gets a new value, and what is the new value? The second one, yes. And what's the new value? 21. Yeah. So you assign a new value to array 1, and it is the sum of array 0 and array 1 plus 1, which means this gets 21. And then let's look at the array first. What happens in the next step? Which element gets a new value? The third element, because I is now 3. And the new value is 32. So you take 21 plus 10 plus 1, which is 32. And so in the end, when we see that we output the value of array element 2, which is the third element, the answer will be the 32 that we have computed here. Now let's look at the second string and see what happens here. String I equals string I plus 1. So when we initialize string, it actually gets 4 places because it's a 3-letter string, but C infers that a 4th element is being needed for the terminating 0. So we've got A here, R here, T here, and /0 as the 4th element. So that would be element number 4, which we don't have in the integer array, but we do have that in the string character. Now, in the first step of that loop, which again starts at 1, so that would be the second element here, which gets a new value, and it just copies the value from to the right. So the R here will be replaced by T, because that's the element to the right. And in the second step, we move to that element, and it is also being assigned the character to the right, which is the 0 character. So this will be replaced by \0. And nothing else happens. The loop terminates because now we would be moving beyond index number 3. Why did I say 4? It should have been 3. Okay, but we don't move to character number 3 because the loop terminates before we have reached 3. And so you can see that the value of the string array is now A, T, followed by \0. And therefore, when we output the string, the output would be the word or the string at. And the output would then terminate because we've got the 0 character here. So that will be the result of this program. And again, if you don't believe it, or you want to play around with what happens inside of this loop, then this is a complete program that you can implement, and you can test the output and see that this is exactly what you will get as a result. What is important to know is how functions deal with arrays. And they deal with arrays in a different way than with simple data types as parameters. What happens when an array is passed as a parameter to a function is that the function gets the start of the array as the parameter. For example, if you have an integer total and you have a vector consisting of 20 integers, and you want to call a function that I've called sum here, which may sum all the elements in this vector, then what would happen here is that the address of this array is being passed on. It's not that the entire array is being copied. And this is why, for example, in the insertion sort algorithm that I have showed you earlier, the effect of that function was that the original array, whose address was passed as a parameter, was being sorted. So that in the end, when I output the values, you can see that the original, the calling array, has been manipulated by the function. Within the function, we do know the types of elements in the array, because this is part of what you have to tell your C compiler when you write the function, that your parameter is of type int array, but the size of the array is unknown. The system does not know how many elements are in this vector here. It only gets the starting address. It knows that it is an integer from the signature of the function, but it doesn't know that there are 20 elements. And this is why what we typically have to do, since functions do not know how large an array is, we have to pass the size of the array as an extra parameter to the function. This is one possibility. The other possibility would be to include a standard termination value to mark the end of the array. Just like we do in strings, we have the 0 character to mark the end of the array, and every function that takes a character array as input knows that the 0 character means this is the end of the string. You could do the same thing with integers. If you use a value that would never occur as an actual value in an array, such as -1, if you only deal with natural numbers, then you could do the same thing. Or you just pass on the size of the array, so that what we had previously would probably more likely be implemented as you want to sum all the elements in the array vector, and you tell the function that there are exactly 20 values in that array. This is really necessary because since functions don't know the array size, they can't check whether you have been using an invalid subscript. So you can easily define an array of only 20 elements and then try to index the 30th or 40th element in this array. And you should make sure that you don't do this, and you can do this by making sure that the function always knows what the maximum index would be. So this would be the last exercise for today. Implement a function that sums up all elements in an array. So it would be implementing this, what we can also call a prototype of a function that returns an integer value, and it takes an integer array as input, and as second parameter it gets the size of the array. In the interest of time, because I also wanted to get to the last heterogeneous data structure, let me just show you how this can be done. I think it would be clear to everyone that you need a for loop that goes through starting at the beginning of the array to the end of the array and just adding up all the values that you find there. Now in C, this would look like this function here. You have the array, you have the size of the array called dimension, and then you initialize your total sum by 0. And then you have a standard simple for loop that goes from left to right and just adds up all the elements that it finds in the vector, adds it to what you have in total, and in the end returns total. You can see you can do this here only because you do know the dimension of the array, which you really do need in that loop here. Okay, to finish the introduction to arrays, we can also have multi-dimensional arrays such as matrices, and they would be defined in C with the help of this syntax. Here we have a 2x2 matrix of floating point numbers. Here we have an integer matrix of size 3 times 4. And in total, obviously, you have 12 values. Here you have 4 values. Do note that in all dimensions, you always start counting at 0 when you look at the index. So if you wonder, for example, what the element Q01 would be, you have to look into the first row and the second column. And this gives you the element Q01, 2.7. R13 would be 8, because this is row 0, row 1, and the element with index number 3 is the fourth element, 8. You can also access entirely one-dimensional arrays, and for instance, Q1 would be the second row consisting of this array, these 2 elements as the second dimension. You can even initialize multidimensional arrays with the help of nested curly brackets. For instance, a complete initialization that gives you this matrix that we have here for Q, would be defined like this, and then the compiler is able to infer that the size is 2 by 2 by this initialization. Now, when you have matrices or even higher structures of higher dimension, then you can iterate through the elements of a matrix or a cube or an array of higher dimension, either doing it by row or column by column. I would say that row by row is the most common style of iteration. If you have a two-dimensional integer array with n rows and n columns, then you could use these two nested loops to go through the elements row by row and then access an individual element through the first dimension row, the second dimension col. But you can also use an outer loop that goes through every column and an inner loop that goes through every row, and then access the same elements in this way. There's a nice little exercise in this week's homework, which asks you to implement functions that are a little more interesting and have to do with matrix operations, a little more interesting than just summing up the values of a vector, as we have seen earlier, where you can see how to use exactly this style of iteration to perform these matrix operations. Last sidetrack for today, because we will also be using it for the heterogeneous structures that we will finally be looking at for the last couple of slides. C allows us to define new data types, or giving names to an existing data type via the keyword typedef. The general syntax would be typedef. You define a new data type, you give a name to a data type. You define, you take an existing data type and you give it a new name. And this would be then the second argument of this typedef. For instance, you can say that when I say temperature, I actually mean this standard basic data type float. Float is an existing type, and temperature would be a new name for exactly the same type. Why would you want to do this? I will show you on the next slide. With arrays, it would be a bit more complicated. The new name that you want to use is called matrix here, and the existing type would be integer array of dimension 2020. And the required syntax is exactly the one that you see here. So you can't write int 2020 and define this as matrix, but you would say integer, then the new name, matrix, and the required dimension. And then from then on, you can use the word matrix to define variables, for example. And the system would know that you want to give it a 20 by 20 integer matrix. Why does it make sense to use these typedefs? It can be used to give meaningful names to value types. For instance, you can use just numbers, but then a reader of a program might wonder whether a given number is indicating a temperature, for example, or a dollar value or something else. You make it easier by just using these names in a similar way we have been using symbolic constants to make your program more readable. The other thing is, again, like with symbolic constants, that it allows for an easy change to the underlying type. For example, if you have defined real as float, and then everywhere you're using real, for example, for a complex calculation, which takes real numbers as input and returns real numbers and uses variables of this format. If at some point you find out that floating points are not precise enough, then all you have to do is to change this occurrence of float by double. And then you get double precision floating points without you having to change every occurrence of real number in your program. So that allows you, even for these simple data types, to maintain your program when you want to make changes, and for more complex constructs that you're building, you can package up complex types for easy reuse. Matrix is a simple example. We will see many, many other examples as we are looking at more interesting data structures throughout this course, including the last thing that we will be looking at, namely heterogeneous data types in C, or so-called structures. Structure is a collection of variables, perhaps and quite often of different types. And these collections of variables of possibly different types, they are then grouped together under a single name. The reason for doing this is that it helps us organize complicated data into manageable entities, and it does expose very nicely the connection between data within an entity. And again, that makes reading, writing, and maintaining a program so much easier if you do that systematically. In C, these heterogeneous collections of objects are defined using the struct keyword for structures. And here we see a first very simple example that defines a new type, which I call date T, date type. It is common practice to use that capital T at the end of an arbitrary string to indicate that this is the name of a type and not the name of a variable. And I'm defining here a structure which I give the type name date T, consisting of 3 integers, which I call the day, the month, and the year. And that defines a collection of 3 integers as indicating a date, consisting of these day, month, and year values. Now, the nice thing is that you can nest structures inside of each other, so you can start building more and more interesting and complex data types. For instance, here we have a structure, as we've seen earlier, that defines a date as consisting of 3 integers. And another structure is defined here for a data type called time, consisting of 2 integers, one for the hour and one for the minute. And then we can define an even more complex data structure for speeding tickets. This speeding ticket consists of a 7-character array license plate. Note that we do need 7 characters here because in Australia license plates, they have 6 characters, but we always need to make sure that we have the terminating 0 in the string if we want to print it as a string. We might have a double precision number, although it might not be necessary to store this as a double precision for the speed, and a date, D, and a time, T, which in itself is this structure and this structure respectively. And we define this as a ticket type. Now, the way this would be stored in memory would be, if we look at the definition of the ticket type, we had a 7-character array. And that would be the first information that is being stored. Then we have that double precision number for the speed. And as a double precision number, at least on most computers, including the CSE lab computers, would take 8 bytes, whereas CSE lab computer for an integer would only use 4 bytes. But a modern Mac, including this one, they would also be using larger integers for the standard integers, not for floating point numbers and not for double precision numbers, but the number of bytes that are being reserved for a particular type that really does depend on the architecture of the computer that you are using. We will see that in detail also a little later. Double precision standard would be 8 bytes. Then we have 4 bytes for every integer. So for a date, we would have 12 bytes. For hour and minute, we would have another 8 bytes for these 2 integers. Note that here I've said that in order to store this string, the system would reserve 7 bytes for the 7 characters of the array, including the terminating 0 string character. And then it would add 1 so-called padding byte, a single one, to ensure that this whole structure lies on a 4-byte boundary. It wouldn't allow the system, and this has to do with quick access to individual memory cells, it wouldn't allow the 8 bytes for the speed to come directly after that 7 bytes of that string, only because individual chunks have to occur unless they are individual characters, such as floating point numbers or integers, on 4-byte boundaries. Again, I'm only mentioning this at this point. We will look into this in more detail later. Normally, you even don't care about the internal layout since fields are accessed by name. So you wouldn't have to calculate how many bytes you have to advance in order to get one of these values. But you do have these individual names for these fields like plate, speed, D, and T. And we see here how they are going to be used. When you define a structure as typedef, then it does not allocate any memory in itself. What you actually have to do is you have to declare a variable in order to allocate memory. For example, now that we have that data type date t, which consists of 3 integers, day, month, and year, we can say Christmas is a variable of that type, and then we can access the components of the structure using the so-called dot operator. And we can make assignments and can say this year Christmas.day would be the 25th of December and the year 2018. So the individual fields here are accessed with the help of variable, dot, and then the name that you gave these individual fields in your definition of the type. If we look at a more interesting example with the above ticket type, we can declare and use variables in the following way. I'm using a symbolic constant to say that I want to store 1,500 speeding tickets. Then I do type def the ticket T structure consisting of the license plate, the speed, the date, and the time. Then I'm declaring tickets as an array of size 1,500 of type ticket T. And then, assuming that I've filled all the information for all the 1,500 speeding tickets, this would be how I can print them in a nice format by, first of all, accessing every individual ticket's component by saying this is the ith component of the array tickets. And I'm then accessing the plate, the license plate. I'm printing this as a simple string with a placeholder %s, and the speed in a specific format, and then the day, month, and year in this format, so that it would say 31st-7-2018 for today, and then the hour and the minute, followed by a new line so that you would get every speeding ticket nicely formatted in one extra line. With this, just because we are almost out of time, let me skip over the last 2 or 3 slides. I will certainly come back to them at the beginning of the lecture next week. Oh, actually, it was only 2 slides. Wasn't even necessary. But, well, let's skip the last slide, and I will come back to it at the end. What you will always see, and this is what I wanted to show you at the end of every slide set, There is a summary that summarizes everything that I've been talking about, and this is the most important thing that you should have taken out of this lecture. So here we had an introduction to the course, and we looked at basic data types, programming constructs, and data structures in C. And what I also add at the end is suggested reading. This would give you a very specific indication of, if you want to go to the textbook, where you need to look at in order to read anything about the individual topics that I have covered. And let me just encourage you again to, before I post the solutions early next week, to really look at the homework, try to do all the programming exercises in there, and if you have difficulties, come to the help lab on Friday. And with that, I'll see you next week.